Hello. So today we're going to be talking a little bit about matrix operations. We've been talking about systems, system dynamics, and now we're transitioning into how to do solutions for systems and how we can actually implement those types of solutions. I might want to zoom in. Camera angle's a little weird. We don't need to see the top and bottom of the board, do we? Just try to make this a little bit more visible. All right, so matrix operations. And this is also discussing the mathematical study of matrices is called linear algebra. Just so that you're aware, we don't really require you to take linear algebra, but understanding matrices and having a little bit of familiarity with matrices, I feel like it's helpful for anyone. Now, a lot of linear algebra is taught from a very theoretical standpoint. We cut out all the theory and there's just a little bit of meat that we can use in solving system equations using matrices. So first of all, what is a matrix? Okay. If I'm going to be frank, it's not Keanu Reeves. There's not a matrix of people's minds plugged in together that are powering machines. It's not that. Although I still need to see like the last 3 movies that have come out. Different story. I saw the first one, it was good. The matrix is... it's basically just an arrangement of mathematical values. Matrices can also be characters. In programming, you can have a matrix that consists of a number of letters. But here, in our terms, the way that we're going to define it for this class, these are all mathematical. These are equations. A lot of times they're coefficients. Okay? A matrix will look something like this, where you have a certain number of numbers arranged in unique, what are called cells. So here, this one is a cell. Here there are 12 cells in this matrix, and this cell is defined by its row number and its column number. Okay? Give me 1 second. I never remember which comes first. Okay, so it always starts, this right here, we have 1, 2, 3, 4 rows, and we have 1, 2, 3 columns. This would be considered a 4 by 3 matrix. Notice 4 by 3 gives us the number of cells that we have in our matrix, which is a total of 12. Okay, so that's kind of the definition of a matrix. And instead of having numbers, these are scalar numbers, we could have functions. So you have a matrix that's 4x plus 5 and 3e to the negative x, and you can have 0 and 2. You can have actual functions in here instead of having scalars. But the idea is that at each x value, or at each t value, or at each set of x, y, z, t, w values, it's going to generate a matrix of all scalar numbers. So kind of an interesting way of thinking about it. It always boils down to this, but the matrix itself may change based on formulas. We're not going to go that far into matrices. Most of what we're going to be dealing with in this class is actually scalar values for our matrices. So now that we know what a matrix is, let's talk about a vector. A vector has both magnitude and direction. Oh yeah! If you don't get that reference, you should get out of college, go back to school, get a real job, hippie. So here, a vector, well, I like watching myself on the live stream. Hi, me. Hi, Mom. What a vector is it is a matrix that only has one dimension. Okay, and so it's just a special version of a matrix. Technically, you can consider a scalar value to be a special version of a matrix that only has one column and one row. So here we could have a vector that is 0, 1, 2, 3, or it could also be 0, 1, 2, 3. Now these have two very different properties, which we'll talk about a little bit of what the difference is between having a column vector versus having a row vector. We'll get there. Right now we're just covering some basic definitions here. Okay, so when would this be useful? Well, when we have a row of matrices, anytime you do spreadsheet math, you're effectively coming up with a matrix of your own. And some of the columns have useful values. Some of the columns do not have useful values, and that's fine. You know, as long as you know which ones have value and which ones don't, that's okay. But let's say, here's a good example. You are the enemy supreme. You're the head of your HOA. Everyone hates you. I even hate you. That's a joke. But let's say you are the head of your HOA, okay? You have to keep data. So what we'll do is we're going to have different columns and different rows representing information. So some of the data you have to collect are people, like, you know, who all is involved in your HOA. And then we're also going to have to keep track of home prices. We'll have to keep track of tax valuations. So that may be very different from home prices. Age of home, expected value. So here, maybe this individual is doing some renovation, so next year their expected value is going to be significantly different. Okay, and each one of these pieces of data is useful. Now, every one of these home prices is going to be tied to a person. Every one of these tax valuations is going to be tied to a person. Every one of these ages of homes is going to be tied to a person. Whoever owns the home. So these are all kind of independent of each other. And they all depend on who owns the house. So what we can do is we can say, all right, we're going to come up with a spreadsheet where here, this is the people. You know, you've got the Johns, you've got the Marys, you've got the Smiths. Boy, it's really bad when I'm struggling for generic names. You have the Brodericks, because why not? You know, and each one of these people have their own now home prices. All right, let's say that this is an HOA for a trailer park. Okay, so this one's going to be 40K. This one's Mary's living at 42K. The Smiths, they really don't have a nice house. But the Brodericks, they're living in luxury. Ho 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 ho. Those people, they're the fancy group. They smoke cigars, and their cigars are not made out of trash. Okay, so that all has numbers. The next one, tax valuation. Let's say the city just wants money out of everybody, and so it's basically everybody is valued at 80K. Okay, and you get a certain amount of taxes every year based on your tax valuation. Age of home, this may be, maybe there's a 3-year-old trailer, maybe this is a 19-year-old trailer, 14, and then this one will be 56. It's a prim and proper, well taken care of trailer. And then expected value in the next year, 40K. 40K, let's say they're just trashing their property. The Smiths decided to do a renovation. They added an extra dog kennel. And the Brodericks, they just took care of their property. Okay, so every one of these numbers has meaning. Now, if I just go ahead and pull out this number right here, 80K. That was a bad example. Let's go ahead and pull out this number right here, 19. Okay, 19 falls in row 2, column 3. That 19 has a specific value. If I pull out that 19, what does it mean? It means, well, it's the number 19, but that represents the age of home for the Marys. Okay, there we go. Every one of these values has a meaning. If I pull out 30K, it doesn't just mean like, oh, $30,000, whoop-de-doo. Like, it is the price of the Smith's house. And so based on its position both in the row and in the column, every one of these numbers has a unique and special meaning. Okay? Now, we have an issue. I'm gonna go ahead and delete this, and we'll go into another matrix. I'll give you another example. That's one example. It's a pretty easy example. It's just a way of collecting data. Now, some of that data has use to it. Okay, so let's be talking about. Ooh, hey, how you doing? Oh, there we go. I'm back. Inventory. Okay, so we're coming up with an inventory matrix. And let's say it's an inventory matrix for... Boy, I hate the blurry camera. I really do. It's an inventory matrix for ice cream. Okay, so we've got vanilla, chocolate, we have strawberry, I'm sure there are other kinds of ice cream. I am absolutely blanking right now. Pistachio, why not? We have eclectic tastes in ice cream. Very bland, very regular pistachio. Okay, so every one of these has an associated data value that goes along with it. We're talking like, how many carbs? How many carbs per gallon? Per gallon. I don't honestly know these numbers, so I'm gonna guess. We'll say like 320. Let's say chocolate, it's 400. Strawberries, probably even sweeter, and then pistachios we'll throw out. Then you know that each one of these, how many fat grams per gal? Because apparently that's our serving size. It's 1 solid gallon. Like, we don't go lightweights here. It's shovel time. Okay, so here we'll say 90, 50, 80, 40. Just throwing out numbers. And then, you know, each one of these is going to have a protein count. Again, grams. I'm just throwing these out here. 20, 30, 25, 25. Weight per gallon. Okay, and so we can keep going on all of these. All right. 6.2, 8.0, 7.8, 7.0. All right, so these are our numbers. Now, how do we do something with this? Well, what we can do is we can say, all right, I want to add this matrix, but I'm going to say, I want to know how this would change if I add a gallon of chocolate sauce on top of it. Okay? We would have to take every one of these numbers and adjust them for what additional value the chocolate sauce adds. Okay, so I'm just going to take this matrix, which right now is a 4x4, 320, 90, 20, 6.2, 400, 50, 30, 8.0, 420, YOLO, 80, 25, 7.8, 450, 40, 25, 7.0. Okay, that's my matrix that is generated by these. If I go look at 30, 30 represents the number of grams of protein in a gallon of chocolate ice cream. Okay, now I'm going to add a gallon of strawberry sauce. Now the thing about it is, it doesn't matter whether it's vanilla, chocolate, strawberry, or pistachio, what it's being put on. The amount of carbs per gallon of chocolate sauce is going to stay the same. The amount of fat per gallon is going to stay the same. So here all my columns are going to be the same. You're going to notice that. Let's say it's 120 for all of these. 30. And again, 30 represents the number of fat per gallon of chocolate ice cream that would be added by adding a gallon of chocolate sauce. There's a reason why 30 is the same here, 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 and here, is because it's the number of grams that would be added for each one of these flavors. It doesn't add any protein. And the weight per gallon, it's going to be some amount of weight. Let's just call it an even 10. Apparently our ice cream is pretty light and fluffy. It's lighter than sauce. Now if we added these together, we would be adding the number of carbs per gallon of vanilla plus the number of carbs added by adding a gallon of chocolate sauce to it. We'd have a total of 440. 440. Okay, and then we're going to do that per each cell. I can't add this value to this because this is 30 fat grams added to 320 carbs. They're two different quantities. So the placement of the values inside of our matrix actually makes a difference. Okay, what we end up doing is we say cell 1, which is row 1, column 1, can be added to cell 1, which is row 1, column 1. And that produces cell 1, row 1, column 1 of the final matrix. Okay, and then we keep doing this. 90 to 30, so 120. I'm running out of board space. Should have thought about that. Gonna go into, I'm gonna draw it up here. So 440, 120, 20 plus 0 is 20, and then 16.2. Okay, it's a gallon of ice cream plus a gallon of chocolate sauce. And then we keep going. If you're 400, this is 520, this is 540, this is 570. And then 80, 110, 70, and you have 30, 25, 25, and then you have 18, 17.8, and 17. Okay, and so this is the resulting sum matrix. Now, the interesting thing here is that cell 1 of both of these has to add. What if I tried to add a matrix where, like, here we looked at this and we said, okay, 120 for all of these are the same value. If I were to only do a gallon of chocolate sauce, why can't I just add that in and be done with it? Well, the issue with matrix math is that is 120 carbs per gallon of vanilla, and then what, zeros for the rest? That means this adds 0 fat grams if I add a gallon of chocolate sauce to a gallon of chocolate ice cream. That doesn't even make sense. We had to have the exact same dimensions for our two matrices in order to add them, okay? Having a vector and adding it to a matrix of a different dimension actually gives you wrong results because you end up assuming that these are zeros. And that's not right. This first row would be right and everything else would be wrong because it would just be identical to what you already have. That's not true. You can add this matrix to this. This is valid because it has the same dimensions. It's not right, but it has the same dimensions. So the critical rule of adding matrices is they must have the same number of rows and same number of columns. The other piece that you're probably not going to see in a textbook is every one of these cell values has to represent the same thing. They have to be identical in their meaning. Okay, and when you do your matrix operations, when you do add matrices together, most oftentimes you will be given matrices where they already have the same meaning. And all you're doing is just putting them together. So, rule number 1 in addition and subtraction, they must be the same dimension. Now, what if I swap the positions of this? So we'll call this matrix A, which will be represented by an A inside of brackets. We'll call this one matrix B. Is A plus B equal to B plus A? The answer to that is yes. For addition, they're the same. Okay, if I take a gallon of chocolate sauce and I dump it on top of a gallon of each one of these, it's going to give me the same value as if I take a gallon of these and drop it on top of a gallon of chocolate sauce. They're interchangeable. This is an important quantity. You can switch those. That is not true when it comes to matrix multiplication. So, fundamentals of matrix addition, it's pretty simple. You will need to understand this in order to do basic matrix operations though. Okay, so another thing that we can do on our inventory list is, let's say we have, we're coming up with, we have a facility that has certain production capabilities. Okay, so factory production, and you have certain items that you produce, A, B, C, and D. Okay, time to make, cost of making, and we'll have one more column, just the total weight. Okay, so here, let's say this takes 12 minutes, this takes 8 minutes, this takes 16 minutes, this takes 20 minutes. Cost, this will be $2, this will be $4, this will be $6, this will be $8. Okay, and then weight, we'll say that this is 4 pounds, this will be 2 pounds, this will be 1 pound, and this will also be 1 pound. Okay, so here's what we have. These are the 4 items that our facility can produce. Now we get an order in, and the order is, I want 12 item A, I want 4 item B, 0 C, and 2 item D. Okay, so if we're going to add this, every one of these values has to mean the same thing, right? Which means 12 has to be time to make. Well, this one isn't a value, this is a count. I want 12 items of A when I order this. I want 4 items of B. I want 0 items of C. I want 2 items of D. That's not a time value. and that's not a money value. What we're going to do is we're going to multiply these. Okay? So now we're getting into matrix multiplication. Matrix multiplication is itself set up very interestingly. Here, A cross B. A multiplied by B. When we do it that way, what we're doing is, let me make sure. I always seem to get these backwards. Gonna look at my nice board right here. Okay. What you do whenever you do matrix multiplication, the correct way of doing it is you take rows of A crossed with the columns of B. Okay, and that's how you get your output. Okay, so ultimately, every one of these values, let's say you have 12 count of this, you're gonna have 12 times 12 minutes to make, 12 times $2, it'll cost $24 to make. The weight is gonna be 12 times 4 pounds, so you're gonna have 48 pounds of product A in this order, okay? So how do we set this up so that we can do the multiplication? Well, here we have rows of A multiplied by columns of B. The way that I have this set up, if I did something called the transpose, which is where I set my items this way, and then I had these values, time to make, cost to make, weight of making, coming down, I guess going across would just be a flip of this. I could set it like this, and we could do this math just fine according to this operation. We would get a sum total at the end. I don't want to do that. I would rather take this, make this be matrix A, and this be matrix B. Okay, and then what I'm going to do is I'm going to set this, instead of having this be a column, it's going to be a row vector. So it'll be 12, 4, 0, 2. And this is just the definition of matrix math. They could have done this a different way. I chose not to. We just have to abide by the common standards of matrix math. So all I did was I took this and I arranged it into a matrix that I can use to do matrix math with. This one is A, this one is B. When I multiply A by B, what I'm going to get is all of these values. So the resulting vector that I get, A times B, I'm going to multiply each one of these values by these, and then I'm going to sum them together. It's effectively a dot product between this column vector and this row vector. This column vector multiplied by this row vector will be represented by the first column and the first row of my product. So once again, first column of B, first row of A will produce the first column and first row of my final solution. Now here, I only have one row in this matrix, so I'm only going to have one row in my final matrix. I have 4 columns here. No, 3 columns here, which means I'm going to have 1 row and 3 values. Kind of interesting. So to do this matrix multiplication, we have 12 multiplied by 12, so it's 124, plus 4 times 8. 4 times 8 is 32. That is 176. 16 times 0, 176. 20 times 2, that's 216. So my first value is going to be 216. It means the total number of items, the total time to make all of these items is going to be 216 minutes. Okay, that's nice. Total cost of making, 12 times 2 is 24. 4 times 4 is 16. So 24 plus 16 is 40. 0 times 6, 2 times 8, that's 56. It'll cost $56 to make this order. And then 12 times 4 is 48. 48 plus 8 is 56. 0, and then 58. So it'll weigh a total of 58 pounds. Okay, and that's my resulting vector. Now, what's interesting about this was that I took a 4 by 3 matrix, well, I took a 1 by 4 matrix, I should say, and multiplied it by a 4 by 3 matrix, and I got a 1 by 3 matrix. Now, this value is very helpful, because I know how much time it's going to take to produce this lot based on my matrix. I know how much money it's going to cost me to make this matrix, and I could have added extra columns for how much money we're going to charge for each one of these, how much overhead gets charged for each one of these, what is the depreciation for each of the machines for one of these. I mean, you can keep going with all of your column values, but that's ultimately how to do matrix multiplication. So we start with A times B, and now the dimensions of A are 1 by 4, and we cross that with a dimension that is 4 by 3. Here, the 4s are the same. They have to be in order to multiply. Because otherwise, I'm trying to take 12 items of A, like let's say we didn't have a B. 12 items of A, 4 items of B, 0 items of C, and then 2 doesn't mean anything. Like, we don't have 2 items of anything. No, now we have 2 items of D. We have to have that 4th column. 4 by 4, that has to be on the inside. And the resulting value is the 1 by 3 on the outside, which is why we end up with a 1 by 3 matrix as a result. So that's a fast and dirty introduction to some entry-level matrix math items. We're going to talk about solving matrices and how to use matrices as a way of preparing to solve linear algebra problems. We'll talk about that in class on Thursday. So, good luck.